work-energy theorem is one of my favorite topics. It simply states that the work done on something changes the kinetic energy of that something. Yum, common sense. Work equals change in kinetic energy. This is the work-energy theorem. See how nicely it solves this problem. Nellie rides her bike at velocity v along a straight road, and when she notices part of the road ahead is missing, she applies her brakes. The friction between her tires and the road is half the weight of her and the bicycle. How far will she skid? How to start a solution to this problem? First, get a handle on what's going on by drawing a vector diagram. We see there's a weight vector, always, and a normal vector, which is always when a surface is involved. Those are vertical vectors. And in this case, we have a horizontal vector too, a force of friction vector, pointing against the direction of motion. Friction slows the bike. So we have three forces acting on Nellie. What are we looking for? We're looking for distance. So we write d equals. That's a beginning, often the hard part. All we're given are her speed and the amount of friction that will stop her. Is that enough information? What relationship do we know that involves speed and distance? The work-energy theorem. Work equals the change in kinetic energy. From work equals change in kinetic energy, we can say d equals delta ke over F, which more specifically becomes, what is the force in this case? It's the force of friction. So we use the customary lowercase f. And we're told friction is half the weight of Nellie and her bike. That's half mg. So we have, that takes care of the mass, which wasn't given, for we see that m cancels. So apparently the mass doesn't affect the sliding distance. More about that in a bit. So after canceling m and the factors of 1/2, we get, our problem is solved. She slides a distance v squared over g, which hopefully is less than the distance to the missing road surface. Does the equation make sense? The speed squared tells us that if she were traveling twice as fast, her distance of skid would be 4 times as far. That seems right, for twice the speed in the kinetic energy equation tells us kinetic energy is 4 times as much. How does g, the acceleration of gravity, play a role here? G is in the denominator, which means the greater g, the less d. For example, on a planet with more gravity, it seems right that she'd skid a shorter distance, more grab with the surface. Or on a planet with less gravity, she'd come to a farther stop, less grab with the surface. And how about the cancellation of mass? This relates to the force of friction. You've got to know that the amount of friction on something is directly proportional to the normal force on that something. And on a level surface, weight mg and the normal force have the same magnitude. Equal and opposite, actually. So greater normal, or in this case, greater weight, means greater friction, directly proportional, which makes sense. Suppose she and the bike had twice the weight, then she'd experience twice the friction. Twice divided by twice cancels out. Hence we see that mass cancels in this problem. How nice! How frustrating if you think maybe the problem cannot be solved because the mass of Nellie and her bicycle isn't given. That's why it's good practice to solve problems with symbols rather than numbers. With symbols, cancellation becomes evident. Symbols first, numbers later. Let's put some numbers into this problem anyway. Suppose her initial speed is 10 meters per second. You know what? We don't need to know her mass, the bike's mass, or the color of the road surface. All we need to know is the initial speed, and of course that g equals 10 meters per second squared. Then we see the distance she skids is 10 meters. A yum problem? I want to leave you with a question. If the missing road surface were 6 meters in front of Nellie instead of 10 plus meters, what's the maximum speed she can have to stop safely? In other words, V equals what? Until next time, good energy.